You're about to embark on a high-speed journey through the entire CCNA curriculum in just 45 minutes. This video is a power-packed CCNA revision, meticulously designed to efficiently cover the full spectrum of exam topics. We've distilled the expansive CCNA syllabus into concise, information-rich segments, ensuring that every minute you spend with us is packed with value. Each slide in this presentation is crafted to deliver approximately 8 to 10 key points, focusing on the most essential concepts you need to know. To get the most out of this session, we strongly recommend staying fully engaged throughout the video. Keep a notebook handy. You'll want to jot down key concepts, critical details, and any areas you'd like to revisit for deeper understanding after the video. Our primary goal is to help you grasp these concepts, not just memorize them. This deep understanding will be invaluable, not only for your exam success but also as you advance in your networking career. Throughout this video, we'll cover everything from networking basics and the OSI model to more advanced topics like network automation and SDN. This is your whirlwind tour of the CCNA landscape, designed to reinforce your knowledge and pinpoint areas where you might need further study. Whether you're deep into your CCNA studies or gearing up for the final exam, this video is your ultimate resource for a quick and comprehensive review of the entire curriculum. Before we dive in, take a moment to like and subscribe to support our channel. If this video reaches 1,000 likes, we'll create a complete CCNA course, covering every topic in depth from the ground up. Ready to supercharge your CCNA revision? Let's make these 45 minutes count as you consolidate your knowledge and sharpen your skills. Your path to CCNA mastery begins right now. We'll start with networking basics, including types of networks and key devices. Then we'll explore the OSI model and its layers. We'll dive into IP addressing, both IPv4 and IPv6, and tackle subnetting. Routing basics and protocols will follow, including static and dynamic routing. We'll cover switching concepts, VLANs, and spanning tree protocol. Security topics will include ACLs, NAT, and wireless security. We'll touch on DHCP, troubleshooting techniques, and emerging technologies like SDN and network automation. We'll conclude with must-do topics for the CCNA exam and mention some advanced topics not covered in depth. Let's begin our whirlwind tour of CCNA Essentials. A network is a group of connected devices that can communicate. We have LANs for local areas, like offices or homes, and WANs for wider coverage, connecting LANs across large distances. Key devices include routers that direct traffic between networks, switches that connect devices within a network, and hubs that send data to all connected devices. Networks use protocols, which are sets of rules for communication. TCP/IP is the foundation of Internet communication, while Ethernet handles local network connections. Data transmission can be unicast, one-to-one, broadcast, one-to-all, or multicast, one-to-many. In half-duplex mode, devices take turns sending data like a walkie-talkie. Full duplex allows simultaneous sending and receiving, like a phone call. Remember, routers work between networks while switches work within networks. Network topologies define how devices are arranged, including star, mesh, bus, and ring configurations. Collision domains are separated by switches, improving network efficiency, while broadcast domains are controlled by routers. Understanding these basics is crucial for grasping more complex networking concepts and troubleshooting issues in various network setups. The OSI model has 7 layers describing how data moves through a network. From bottom to top: physical data link, network, transport, session, presentation, and application. The physical layer deals with hardware connections and raw data transmission. Data link handles MAC addressing and creates frames. Network manages IP addressing and routing between networks. Transport ensures reliable data delivery using TCP or UDP. Session establishes, maintains, and terminates connections between applications. Presentation formats and potentially encrypts data. Application interfaces directly with software applications. As data moves down the layers, each adds its own header, a process called encapsulation. The reverse happens going up, called decapsulation. Each layer provides services to the one above it. To remember the layers, use the phrase, "Please do not throw sausage pizza away." The first letter of each word corresponds to a layer, bottom to top. Think of encapsulation as wrapping a gift, and decapsulation as unwrapping it. The lower layers 1 to 4 deal with data movement, while upper layers 5 to 7 focus on data processing. The OSI model is crucial for understanding network operations, protocols, and troubleshooting issues at different levels of network communication. An IP address uniquely identifies devices on a network. IPv4 uses 32-bit addresses written as 4 numbers separated by dots. IP classes A, B, and C are for general use, D for multicast, and E for experimental. We have private IP ranges for internal networks and public IPs for internet use. Private ranges start with 10.172 or 192. The subnet mask determines which part of an IP identifies the network versus the host. It's often written in CIDR notation, a compact way to represent the mask. Special addresses include the loopback address for your own device, remember? There's no place like home, and the broadcast address for all devices. The default gateway is the router's IP used to send traffic to other networks. IPv6, the newer standard, uses 128-bit addresses written in hexadecimal. It was developed to address the shortage of IPv4 addresses. When working with IP addresses, you'll use commands like IP protocol configuration on Windows or ifconfig on Linux and Mac to check your configuration. Understanding IP addressing is fundamental for network design, troubleshooting, and implementing network security measures. It's also crucial for configuring network devices and setting up routing protocols. Subnetting divides large networks into smaller subnetworks, improving efficiency, security, and address utilization. It uses bits from the host portion of an IP address to create subnet bits. The subnet mask determines network size and host capacity. In a subnet, the network address is the first address, the broadcast address is the last, and usable host addresses are in between. VLSM, or variable length subnet masking, allows different size subnets within the same network, maximizing address usage. For quick subnet calculations, remember that a /24 gives 256 addresses, and each time you add 1 to the slash, you cut the addresses in half. Always subtract 2 from the total addresses to get the number of usable hosts, accounting for the network and broadcast addresses. Subnetting is crucial for network design, especially in large organizations where efficient use of IP addresses is essential. It helps in creating logical divisions within a network, implementing security policies, and optimizing network performance. CIDR, or classless interdomain routing, extends the flexibility of address allocation and routing. In IPv6, subnetting is simpler due to the vast address space, typically using the first 64 bits for the network portion. Practice subnetting regularly. It's a fundamental skill for network administrators and a common topic in CCNA. Routing is the process of forwarding data packets between different networks based on IP addresses. We have static routing with manually configured routes, good for small, stable networks, and dynamic routing that learns routes automatically, ideal for larger, more complex networks. A routing table contains destination networks, next hops, exit interfaces, and metrics. The routing process involves receiving a packet, checking its destination IP, consulting the routing table, and forwarding the packet to the next hop or exit interface. Static routing is like using a paper map, while dynamic routing is more like a GPS that updates automatically. Key concepts include administrative distance, which determines the trustworthiness of a route source, lower is better, and metrics, used to select the best path when multiple routes to the same destination exist. Remember the phrase longest match wins, meaning the most specific route is always chosen. The default route, often referred to as the gateway of last resort, is used when no specific route matches the destination. Dynamic routing protocols include RIP, OSPF, EIGRP, and BGP, each with its own characteristics and best use scenarios. Interior gateway protocols, IGPs, like OSPF and EIGRP, are used within an organization, while exterior gateway protocols, EGPs, like BGP, are used between different organizations. Understanding routing is essential for designing robust, scalable networks and troubleshooting connectivity issues in complex network environments. Dynamic routing protocols automate the process of sharing route information between routers, essential for large and complex networks. The main protocols include RIP, EIGRP, OSPF, and BGP. RIP is simple but slow, using hop count as its metric with a maximum of 15 hops. EIGRP, a Cisco proprietary protocol, offers fast convergence and efficient bandwidth usage, using a composite metric of bandwidth, delay, load, and reliability. OSPF, a link state protocol, is excellent for large networks and uses a hierarchical design with areas, basing its metric on interface cost. BGP is used for internet routing, making decisions based on complex path attributes and policies. We distinguish between interior gateway protocols like RIP, EIGRP, and OSPF, used within an organization, and exterior gateway protocols like BGP, used between organizations. Link state protocols like OSPF have knowledge of the entire network topology, while distance vector protocols like RIP only know the next hop. Key concepts include convergence time, how quickly routers agree on the network topology, and route redistribution, the process of sharing routes between different protocols. Remember, IGP is for inside routing, EGP for outside. Routing loops are prevented by mechanisms like split horizon and route poisoning. Switching operates at layer 2 of the OSI model, focusing on MAC addresses to forward frames within a local area network. The core of switching is the MAC address table, also known as the CAM table, which maps MAC addresses to switch ports. Switches learn these mappings dynamically through a process called MAC address learning. The switching process involves 3 key steps: learning source MAC addresses, forwarding frames to known destinations, and flooding unknown unicast frames to all ports except the source. We have Layer 2 switching, which operates based on MAC addresses, and Layer 3 switching, which can also handle IP routing. VLANs are used to segment networks logically, improving security and performance. Switches create separate collision domains for each port, but a single broadcast domain for the entire switch unless VLANs are used. Port security is a feature that limits the number of MAC addresses allowed on a port, enhancing network security. Spanning tree protocol prevents loops in switched networks, crucial for maintaining network stability. Trunking allows multiple VLANs to traverse a single link between switches, essential for efficient VLAN communication across multiple switches. Remember, Layer 2 deals with MAC addresses, while Layer 3 deals with IP addresses. Virtual LANs or VLANs logically segment a physical network into multiple broadcast domains. They improve security, reduce broadcast traffic, and enhance network management. The 802.1q standard is used for VLAN tagging on trunks, adding a 4-byte tag to Ethernet frames to identify the VLAN. This tag includes a 12-bit VLAN ID, allowing for up to 4,094 VLANs. The native VLAN is the one that doesn't get tagged on a trunk link, typically VLAN 1 by default, though it's recommended to change this for security reasons. Inter-VLAN routing is required for communication between different VLANs, typically done by a Layer 3 switch or router. We have static VLANs, which are manually assigned to ports, and dynamic VLANs, which can be assigned based on MAC address or other criteria. VLAN Trunking Protocol, or VTP, is a Cisco proprietary protocol used to distribute VLAN information across switches, though it should be used cautiously in production environments. When configuring VLANs, you'll create them, assign them to ports, and set up trunks. VLANs effectively create separate virtual switches within a single physical switch. Always use 802.1q tagging to ensure your VLANs are recognized across the network, and be mindful of VLAN hopping attacks in your security considerations. Spanning tree protocol is a crucial Layer 2 protocol that prevents loops in switched networks while maintaining redundancy. STP creates a loop-free logical topology by electing a root bridge and determining the best path to it from each switch, blocking redundant links. The protocol uses Bridge Protocol Data Units, BPDUs, to exchange information between switches. STP defines several port states: blocking, listening, learning, forwarding, and disabled. The transition through these states helps prevent temporary loops during topology changes. Rapid Spanning Tree Protocol, RSTP, offers faster convergence than traditional STP. Per VLAN spanning tree PVST+, runs a separate STP instance for each VLAN, allowing for better load balancing. Multiple spanning tree MST combines multiple VLANs into a single STP instance, reducing CPU load on switches. Key STP parameters include bridge ID, path cost, and port ID, which determine the STP topology. STP enhancements like port fast, BPDU guard, and root guard provide additional stability and security. Remember, STP is your network safety net against broadcast storms and other loop-related issues. Regular monitoring and tuning of STP are essential for maintaining a stable and efficient switched network. Etherchannel is a port link aggregation technology that allows you to bundle multiple physical Ethernet links into a single logical link. This technology is crucial for increasing bandwidth and providing redundancy between switches, routers, and servers. Etherchannel can combine up to 8 ports into a single logical connection. There are 2 main protocols used for negotiating Etherchannel: LACP, Link Aggregation Control Protocol, which is an IEEE standard, and PAGP, Port Aggregation Protocol, which is Cisco proprietary. Static Etherchannel can also be configured without a negotiation protocol. Load balancing in Etherchannel can be based on source or destination MAC addresses, IP addresses, or port numbers. All ports in an Etherchannel must have consistent speed and duplex settings, and belong to the same VLAN or be configured as trunks. Etherchannel provides increased bandwidth, improved redundancy, and simplified management as multiple physical links appear as one logical link to upper layer protocols. When troubleshooting Etherchannel, verify consistent configurations across all ports and check for mismatched protocols or settings. Think of Etherchannel as creating a wider highway for your network traffic, allowing for more capacity and providing alternate routes if one path fails. IP routing protocols are essential for dynamic route discovery and maintenance in networks. RIP, or Routing Information Protocol, is a simple distance vector protocol using hop count as its metric, but it's limited to 15 hops and has slow convergence. EIGRP, Enhanced Interior Gateway Routing Protocol, is a Cisco proprietary advanced distance vector protocol that uses a composite metric for fast convergence and efficient bandwidth usage. OSPF, Open Shortest Path First, is a link state protocol that supports large networks through its area concept and uses cost as its metric. BGP, Border Gateway Protocol, is a path vector protocol used for internet routing, making decisions based on paths, policies, and rules. Interior Gateway Protocols, IGPs, like RIP, EIGRP, and OSPF are used within an organization, while Exterior Gateway Protocols, EGPs, like BGP, are used between organizations. Link state protocols have knowledge of the entire network topology, while distance vector protocols only know the next hop. Route redistribution allows sharing routes between different protocols. Convergence time, the speed at which all routers agree on the network topology, is a critical factor in protocol selection. Remember, RIP is simple but limited, OSPF is scalable and widely used, EIGRP offers fast convergence but is Cisco-specific, and BGP handles the complex routing of the Internet. Access control lists are powerful tools for filtering network traffic and implementing security policies. ACLs filter packets based on specified criteria and are used on routers and firewalls. Standard ACLs filter based on source IP address only and are typically placed close to the destination. Extended ACLs can filter based on source and destination IP, protocol, and ports, and are usually placed close to the source. Numbered ACLs use numbers for identification, while named ACLs use descriptive names for easier management. Wildcard masks in ACLs specify IP address ranges, working as the inverse of a subnet mask. The implicit deny at the end of every ACL means all traffic not explicitly permitted is denied. ACLs can be applied inbound or outbound on interfaces. They're used not only for security, but also for traffic shaping and controlling routing updates. When placing ACLs, remember the phrase, extended close to the source, standard close to the destination. Be cautious when modifying ACLs on production networks, as mistakes can disrupt traffic flow. The established keyword can be used in extended ACLs to permit return traffic for TCP connections. Always test ACLs thoroughly before deployment. Remember, ACLs are your traffic cops controlling what goes in and out of your network. NAT translates private IP addresses to public IPs, essential for conserving public IP addresses and enhancing network security. There are several types of NAT. Static NAT provides a one-to-one mapping between inside and outside addresses, useful for servers that need consistent public addressing. Dynamic NAT uses a pool of public IPs for translation, allocating them as needed. PAT or NAT overload maps multiple private IPs to a single public IP using different ports, the most common form of NAT in home and small business networks. Inside local refers to the private IP address inside the network, while inside global is the public IP representing the inside device. Outside local is how inside hosts see an outside device, and outside global is the actual public IP of an outside device. NAT terminology can be confusing, so think of inside as your private network and local as the private addressing scheme. NAT is typically avoided in IPv6 due to the large address space available. When configuring NAT, you'll define inside and outside interfaces, create access lists to specify which addresses to translate, and apply the NAT rules. While NAT provides a layer of security by hiding internal addressing, it can complicate some protocols and troubleshooting. Remember, NAT is like a translator between your private network language and the public internet language. DHCP automatically assigns IP addresses and other network configuration parameters to devices on a network. The DHCP process follows 4 steps, often remembered as DORA: discover, offer, request, and acknowledge. A client broadcasts a discover message, available DHCP servers respond with offers, the client requests a specific offer, and the chosen server acknowledges and provides the IP configuration. DHCP leases have a time limit, after which the client must renew the lease or request a new IP. DHCP scopes define the range of IP addresses available for assignment. Besides IP addresses, DHCP can provide additional options like default gateway, DNS servers, and domain names. For clients on different subnets than the DHCP server, DHCP relay agents forward DHCP requests across the routers. DHCP can provide both dynamic assignment for temporary use and reserved addresses for specific devices. DHCP snooping is a security feature that prevents unauthorized DHCP servers from operating on the network. When troubleshooting DHCP, common issues include address conflicts, exhausted scopes, and misconfigured relay agents. Think of DHCP as an automated receptionist, assigning room numbers, IP addresses, to guests' devices as they enter your network hotel. IPv6 is the next-generation IP protocol with a vastly larger address space, using 128-bit addresses typically written in hexadecimal notation. An IPv6 address is divided into 8 16-bit blocks, separated by colons. IPv6 was developed to address the shortage of IPv4 addresses and provides enhanced features for security, auto-configuration, and simplified header structure. Address types include global unicast, publicly routable, link local for communication within a single network segment, and anycast, one-to-nearest communication model. IPv6 introduces stateless address auto-configuration, SLAAC, allowing devices to configure their own IPv6 addresses without a DHCP server. The Neighbor Discovery Protocol (NDP) replaces ARP in IPv6, handling address resolution, router discovery, and network redirects. IPv6 subnetting is simpler, typically using the first 64 bits for the network portion. IPv6 specific routing protocols include RIPNG, OSPF v3, and EIGRP for IPv6. Dual-stack configurations allow running IPv4 and IPv6 simultaneously on the same network, facilitating gradual transition. While IPv6 adoption has been slow, it's crucial for future internet growth and IoT expansion. Remember, IPv6 is not just about more addresses. It's a fundamental upgrade to the Internet protocol with built-in features for the modern, connected world. Wireless networking has become ubiquitous, with Wi-Fi standards evolving from 802.11, a divided by B divided by G to newer, faster standards like 802.11n, AC, and AX Wi-Fi 6. These standards operate in different frequency bands: 2.4 GHz, more crowded but longer range, and 5 GHz, less interference, higher speeds, shorter range. The Service Set Identifier (SSID) is the network name that identifies a wireless network. Wireless channels are specific frequencies within the band, used to reduce interference between nearby networks. Encryption is crucial for wireless security, with options including WEP, obsolete and insecure, WPA, WPA2 current standard, and WPA3 latest, most secure. Access points (APs) allow wireless devices to connect to a network, while wireless controllers provide centralized management of multiple APs. Roaming allows clients to move seamlessly between access points in the same network. Site surveys are essential for assessing coverage and interference to optimize AP placement. MIMO, multiple input, multiple output, technology uses multiple antennas to improve performance. Beamforming focuses the wireless signal towards specific receiving devices. Remember, wireless networks extend your LAN's reach, but proper security measures are crucial to prevent unauthorized access. Network security is about protecting network data and resources from unauthorized access and attacks. Firewalls are the first line of defense, filtering traffic between networks based on predefined rules. Intrusion detection systems, IDS, monitor network traffic for suspicious activity, while intrusion prevention systems, IPS, can automatically block detected threats. Virtual private networks, VPNs, create secure, encrypted connections over public networks, essential for remote access and site-to-site connectivity. Encryption protects data confidentiality, with common methods including AES, DES, and RSA. Authentication, authorization, and accounting, AAA, systems control access to network resources, often implemented through protocols like Radius or TCAX+. Access control lists, ACLs, on routers and switches provide an additional layer of traffic control. Common network attacks include distributed denial of service, DDoS, phishing, and man-in-the-middle attacks. Security best practices include using strong passwords, regularly updating and patching systems, implementing principle of least privilege, and continuous monitoring. Network segmentation, including the use of VLANs and firewalls, can limit the spread of security breaches. Remember, network security is not a one-time setup, but an ongoing process of assessment, implementation, and adaptation to new threats. Firewalls are critical components of network security, acting as a barrier between trusted internal networks and untrusted external networks. Packet filtering firewalls, the most basic type, filter traffic based on predefined rules examining IP addresses, ports, and protocols. Stateful inspection firewalls track the state of network connections, providing more intelligent filtering than simple packet filtering. Application layer firewalls, also known as proxy firewalls, can inspect traffic at the application layer, offering more granular control and the ability to understand context. Next-generation firewalls, NGFW, combine traditional firewall capabilities with other network device filtering functionalities such as an IPS and application control. Zone-based firewalls divide the network into security zones and control traffic between these zones. Network address translation (NAT) is often implemented on firewalls, hiding the internal network structure. A DMZ demilitarized zone is an isolated network segment for hosting public-facing services, adding an extra layer of security. Firewall policies define the rules for allowed and blocked traffic, and should follow the principle of least privilege. Logging and monitoring of firewall activity are crucial for detecting unauthorized access attempts and troubleshooting. When implementing firewalls, consider the balance between security and usability, and regularly review and update firewall rules to adapt to changing network needs and emerging threats. Virtual private networks create secure connections over public networks, essential for remote access and site-to-site connectivity. There are two main types of VPNs. Site-to-site VPNs connect entire networks to each other, while remote access VPNs allow individual users to connect securely to a network. VPNs use tunneling protocols to encapsulate data, with common protocols including IPsec, SSL/TLS, and L2TP. IPsec, Internet Protocol Security, provides strong security at the network layer and is often used for site-to-site VPNs. SSL VPNs operate at the application layer and are popular for remote access due to their ease of use and compatibility with web browsers. Encryption protects data within the VPN, with AES being a widely used, strong encryption method. Authentication in VPNs can use pre-shared keys, digital certificates, or integrate with existing authentication systems. VPN concentrators are devices that handle multiple VPN connections, important for organizations with many remote users. When configuring VPNs, key considerations include choosing the appropriate protocol, ensuring strong encryption and authentication, and managing key exchange. While VPNs provide excellent security, they can introduce some performance overhead due to the encryption and tunneling processes. Remember, VPNs are like secure tunnels through the public internet, protecting your data as it travels between points. Wireless networks are inherently more vulnerable to attacks than wired networks, making wireless security crucial. Early wireless security used WEP, wired equivalent privacy, which is now considered highly insecure and easily cracked. WPA, Wi-Fi protected access, improved upon WEP, with WPA2 becoming the standard for many years. WPA3 is the latest standard, offering enhanced protection against brute force attacks and improved encryption. The 802.1x standard provides port-based network access control and is often used with radius servers for enterprise-grade authentication. Rogue access points, unauthorized APs connected to the network, pose significant security risks and should be actively detected and eliminated. MAC address filtering can provide a basic level of access control, but can be circumvented, and is not a substitute for strong encryption. Wireless intrusion prevention systems, WIPS, monitor for and prevent unauthorized wireless access attempts. Pre-shared keys, PSK, are commonly used in small networks but can be vulnerable if the key is compromised. Enterprise modes of WPA2 and WPA3 use individual user authentication for improved security. Regular security audits, including wireless site surveys, help identify vulnerabilities and unauthorized devices. When implementing wireless security, consider the balance between security and usability, and educate users about safe wireless practices. Remember, securing your wireless network is like locking the windows in your house. It's an essential part of your overall security strategy. Network troubleshooting is a critical skill for any network professional. The troubleshooting process typically follows these steps. Identify the problem, gather information, analyze the data, propose a solution, implement the solution, and verify the result. Key tools for troubleshooting include ping for testing basic connectivity, traceroute for identifying the path packets take to reach their destination, and various show commands on network devices. Common issues include IP configuration problems, such as incorrect IP addresses, subnet masks, or default gateways. DNS issues can cause name resolution failures, leading to connectivity problems. Routing issues like misconfigured or missing routes can cause network failures. In switched networks, problems with VLANs, spanning tree protocol, or port security can disrupt communication. For wireless networks, interference, weak signals, or misconfigured security settings are common culprits. When troubleshooting, start with the simplest explanations and work your way up the OSI model. Document your troubleshooting steps and solutions for future reference. Remember to check physical connections first. Many problems stem from loose cables or powered-off devices. Effective troubleshooting requires a systematic approach and a good understanding of network fundamentals. Network administrators frequently encounter a range of common issues. Connectivity problems often stem from IP addressing errors, cabling issues, or routing misconfigurations. IP address conflicts, where two devices are assigned the same IP, can cause intermittent connectivity problems. DNS resolution failures can prevent access to websites or services, even when the underlying network is functional. Slow network performance might be caused by network congestion, faulty hardware, or misconfigured quality of service (QoS) settings. Routing loops, often caused by incorrect routing configurations, can lead to severe packet loss and network instability. In switched networks, issues with VLANs, spanning tree protocol, or port security can cause unexpected behavior or network outages. Wireless connectivity problems frequently involve interference from other devices, weak signals due to distance or obstacles, or misconfigured access points. Security breaches, including unauthorized access attempts, malware infections, or data theft, require immediate attention and remediation. Configuration errors on network devices can lead to a wide array of issues, from minor performance problems to complete network failures. Hardware failures, while less common in modern networks, can still occur and may require physical inspection and replacement of faulty components. When addressing these issues, a methodical approach and thorough documentation are key to efficient resolution and prevention of future occurrences. Network automation reduces manual tasks and increases efficiency. Python is popular for scripting and network automation. Ansible automates device setup and configuration changes. REST APIs allow programmatic interaction with network devices. Software-defined networking (SDN) centralizes network management, separating control and data planes. Network configuration protocols like netconf and restconf standardize device management. As networks grow more complex, automation becomes essential for efficient, scalable operations. While not heavily tested in CCNA, understanding automation concepts is valuable for modern networking. Software-defined networking represents a paradigm shift in network architecture and management. SDN separates the control plane decision-making from the data plane packet forwarding, centralizing network intelligence and control. This separation allows for more flexible, programmable, and dynamic network management. SDN controllers such as OpenDaylight or Cisco DNA Center provide centralized management of the network, making decisions about traffic flow and communicating these decisions to network devices. The OpenFlow protocol is commonly used to enable communication between SDN controllers and network devices, though other protocols exist. Network virtualization, a key concept in SDN, abstracts physical network resources to create virtual networks, improving flexibility and resource utilization. Overlay networks, which run on top of physical networks, are frequently used in SDN implementations to create logical network topologies. API-driven networking allows for programmatic control of network devices, enabling automation and integration with other systems. Benefits of SDN include increased network flexibility, improved scalability, simplified management, and potentially reduced costs. However, SDN also presents challenges, including complexity in implementation, potential single points of failure with centralized controllers, and the need for new skills in network teams. SD-WAN, Software-Defined Wide Area Network, applies SDN principles specifically to wide area networks, offering improved performance and cost efficiency for distributed organizations. As networks continue to evolve, understanding SDN principles becomes increasingly important for network professionals. Effective network management uses various tools. SNMP collects data from devices for monitoring. Syslog provides centralized event logging. NetFlow analyzes traffic patterns. Network monitoring tools track performance and health. Configuration management tools help maintain device settings. When selecting tools, consider scalability, integration capabilities, and specific network needs. While detailed knowledge of these tools isn't critical for CCNA, understanding their purposes and basic functionality is useful for network operations. Cloud networking involves infrastructure and technologies enabling cloud computing. Key concepts include public, private, and hybrid clouds, and service models like IaaS, PaaS, and SaaS. Virtual private clouds (VPCs) create isolated environments within public clouds. SD-WAN optimizes connectivity to cloud services. Security considerations include data protection and access control. Cloud networking offers scalability and flexibility, but requires new skills from IT teams. While not a major CCNA focus, Basic cloud concepts are increasingly relevant in modern networks. Network monitoring and logging are critical for maintaining network health, performance, and security. Monitoring involves continuously tracking the status and performance of network devices and traffic, while logging records events and activities for later analysis. Simple Network Management Protocol (SNMP) is widely used for monitoring network devices, collecting data on performance, usage, and health. Syslog provides a standardized way for network devices to send log messages to a central server, crucial for troubleshooting and security analysis. NetFlow and similar technologies analyze network traffic flows, helping identify patterns, anomalies, and potential security issues. Security Information and Event Management (SIEM) systems combine logging and monitoring capabilities with advanced analytics for comprehensive security monitoring. Log analysis involves reviewing logs to identify and troubleshoot issues, often using automated tools to handle large volumes of data. Key performance metrics to monitor include bandwidth utilization, latency, packet loss, and device resource usage, CPU, memory. Alerts and notifications can be configured to provide automated warnings of potential network issues, allowing for proactive problem resolution. Capacity management uses monitoring data to ensure the network can handle current and future traffic loads. When implementing monitoring and logging, consider factors such as data retention policies, scalability of the monitoring solution, and integration with other network management tools. Regular review and analysis of monitoring and log data can provide valuable insights into network trends, potential improvements, and early warning of developing issues. Remember, effective monitoring and logging are not just about collecting data, but about turning that data into actionable insights for network optimization and troubleshooting. While we couldn't cover everything in depth, be aware of these important topics. WAN technologies like PPP, Frame Relay (MPLS), and Metro Ethernet for connecting distributed sites. Advanced quality of service concepts, including traffic shaping, policing, and queuing mechanisms. Infrastructure services such as DNS, NTP, Syslog, and SNMP. Deeper dive into IPv6, including dual-stack implementations, tunneling techniques, and NAT64. IPv6 routing protocols. OSPF v3, EIGRP for IPv6, and RIPNG. Advanced security topics like AAA, firewalls, and intrusion detection/prevention systems. Software-defined networking concepts, including controllers and integrations. Infrastructure management tools like Cisco DNA Center. Network automation using Python and Ansible. These areas, while not covered today, are valuable for a comprehensive networking understanding. Additional topics to explore further include advanced network security setups using Radius and TCAX+, complex threat mitigation strategies involving IDS/IPS, and advanced firewall configurations. In-depth study of SDN controllers and API-driven networking. Advanced QoS techniques for traffic shaping, classification, and marking. Detailed configurations and use cases for various WAN technologies. Comprehensive understanding of infrastructure services like DNS, NTP, Syslog, and SNMP. Advanced IPv6 topics, focusing on transition mechanisms, routing protocols, and NAT64 implementations. While these topics weren't covered in our review, they're important for a deeper understanding of modern networking. As you progress in your studies, allocate time to explore these areas to build a well-rounded networking expertise. Focus on these critical areas for CCNA success. Master subnetting calculations for IPv4 and IPv6 practice until it's second nature. Understand routing protocols, RIP, OSPF, EIGRP, and BGP basics. Be prepared to configure and troubleshoot VLANs and trunking. Write and apply both standard and extended access control lists. Grasp spanning tree protocols operation and configuration to prevent layer 2 loops. Set up network address translation and port address translation for internet access. Learn IPv6 fundamentals including addressing, SLAAC, and basic routing. Configure DHCP for automatic IP assignment. Secure wireless networks using WPA3 and 802.1x. Develop strong troubleshooting skills using ping, traceroute, and show commands. These topics form the core of CCNA knowledge and are likely to be heavily tested. As we conclude our whirlwind tour of the CCNA curriculum, let's recap the essential points. We've covered the core of networking, from the OSI model and IP addressing to advanced topics like SDN and network automation. Key areas include routing protocols such as OSPF and EIGRP, switching concepts like VLANs and STP, and critical security measures including ACLs, firewalls, and VPNs. We've also touched on the growing importance of IPv6, cloud networking, and virtualization. Remember, the CCNA isn't just about memorization. It's about understanding how networks function in the real world. Focus on the must-do topics we've highlighted, but don't lose sight of the bigger picture. Hands-on practice is crucial. Use labs and simulators to reinforce your knowledge. As you prepare for the exam, concentrate on mastering fundamentals like subnetting and the OSI model, understanding routing and switching protocols in depth, grasping security concepts and their practical applications, familiarizing yourself with troubleshooting methodologies, exploring emerging technologies like SDN and network automation. The field of networking is ever evolving, so your learning journey doesn't end here. Continue to explore the advanced topics we couldn't cover in depth, and stay updated with the latest developments. Thank you for your attention during this intensive review. Remember, the knowledge you've gained here forms a solid foundation for your networking career. Good luck with your studies and your CCNA exam. You've got this. Also, before leaving, we'd love to hear about your CCNA journey. Let us know in the comments if this review helped you achieve your CCNA certification. Your success stories inspire us and help other learners in the community. And if this video didn't quite meet your needs, we'd appreciate your feedback too. Your input helps us improve and create better content for future aspiring network professionals.